Hello, I'm Alexander Petrovsky and I will be presenting you our work on Fourier neural operator-based framework for continuous adaptive control. And when we are talking about built-in controllers, there are usually three main approaches, with the first one being model-driven control, which is basically when you have an analytical model of the system and you use it to calculate the best possible next action depending on the current state or a history of observations. And the main advantage of this approach is its reliability, because you can compute in advance the estimate of controller's performance, and you can be certain that the system won't be driven into some dangerous, crazy state the moment you plug this controller into it, and that's why it is extensively used for industrial applications. However, there is a significant limitation of this approach, which is rigidity of the controller, because some kind of model reality mismatch always exists, and in this case the model is fixed. So when the process is non-stationary, or when it is very complex and there are a lot of factors which are hard to account for, or even when equipment degrades, the performance will drop and the control will be suboptimal. As an alternative, there are data-driven control methods that, with reinforcement learning being probably the most famous and popular among them, because it learns directly from experience through trial and error. It needs no model at all. It is adaptive by definition, and a lot of works on reinforcement learning have provided us with guarantees that eventually the agent will converge to an optimal policy given enough exploration and, of course, capacity to learn the system. However, in reality, they are inapplicable to real-world systems, especially the ones with high risks because of horrible sample inefficiency, poor generalization, and even fundamental exploration trade-offs that the agent needs to explore the system, doing suboptimal decisions in order to understand how it works and in order to perform optimally. And that's why hybrid control methods are actively being researched, because they have this potential to combine the advantages of both worlds. In our study, we decided to focus on bioprocesses because of their complexity. They are stochastic, nonlinear, partially observable, non-stationary. They have high operation and failure cost, delayed responses, and so on. However, there are still several features that we can take advantage of. Namely, they are all backed by some physical processes which are quite isolated, and this makes them quite decently modeled with partial differential equation systems. And as a rule, changes in their states are gradual. And neural operators are a novel architecture that extends regular neural networks to functional spaces and allows to uncover complex relations between variables by utilizing special transforms, for example, Fourier transform, wavelets, spherical harmonic transform, and so on. And depending on the transform we choose, we have an ability to exploit some prior knowledge of the system and guide the model towards where it should look for relations. And Fourier neural operators are the most famous member of this family because of many successful applications in quite complex and non-trivial tasks like weather prediction, plasma physics, fluid dynamics, optimal transport problems, and so on, because it is very suitable for accurate and efficient data-driven modeling of systems with partial differential equation based dynamics, especially when it is slow, because Fourier neural operators have built-in low-pass filter. And all of this while they remain fully differentiable and tunable neural networks. And as to our knowledge, there was no such studies before, we decided to develop a framework that could utilize all the advantages and benefits of Fourier neural operators in the context of adaptive control. So here we first obtain an environment surrogate from historical data which is available as a rule. We integrate this surrogate into the agent to do dreamer-like environment rollouts, so basically predict several steps into future, and we pre-train this agent on this world model because it is a full-fledged environment surrogate, and after integration to the real system, and apart from updating the policy network, critic network, as it is usually done in reinforcement learning, we also update the world model. And the agent itself is an extension of popular twin-delayed deep deterministic policy gradient algorithm, DD3 in short, and it is amended with dreamer-like rollouts, which allow to predict the future within a short horizon. And the policy network tries to optimize both for model-free critic and FNO-based loss, so optimize for both immediate performance and safety and long-term rewards, avoiding dead ends and so on. And world model updated as new evidence arise in a continual learning fashion, and so on. We have also implemented an experiment testbed, which is based on highly accurate simulator for penicillin fermentation, and we will compare our algorithm against advanced model predictive controller implemented by authors of this benchmark, pure reinforcement learning, so DD3 without any additions as a model-free baseline, and an ablation study with an offline RL to evaluate the performance we get from applying Fourier neural operator instead of some other techniques, and non-operator version to evaluate the actual gain we receive from utilizing the ability of the system to be properly modeled by Fourier neural operator. And we expect the agent to perform safe operation from the very beginning, to eventually overcome model reality mismatches, so adapt to a real system. It is expected to perform better than the agent obtained from offline pre-training because of FNO advantages, and perform better than advanced MPC because of its continual learning and flexibility, moving us closer to easily implementable, reliable, and smart control systems for complex bioprocesses. Thank you.